Hocam mikrofonunuz kapalı.
Şimdi geliyor mu sesim?
Geliyor.
Tamam. So we can we know that.
Hocam ekran yok ama bu sefer de.
Şaka mı bu gerçekten ya? İnternetten düşmüş. Telefondan bile telefon da yetmiyor yani. So we know that Fn is in theta Gn for n is equal to b to the power k, for k is at least 0 and b is greater than 1. Then we said that f b to the power n is in theta g to the power theta g b to the power n for n in the set of natural numbers. So it means actually for all n. Okay. We want to show that Fn is in theta Gn for all n. For this, first I will make some definitions, okay? We say that a function Hn is called eventually non-decreasing if there exists an integer n0 such that Hn is less than or equal to Hm whenever m at least n0. Okay, so this is the definition. We say that a function is eventually non-decreasing. It means that, let's say that this is such a function Hn. Some things might happen here, but there is some point such that from that point onwards it never decreases. Okay, we say that if there exists an integer such that at least after n0, okay, an integer n0 there exists such that whenever m is greater than n, Hn is less than or equal to Hm. So there is some point, it may fluctuate a little bit up until some point, but from some point onwards, it's always non-decreasing, okay? It's eventually non-decreasing. So after some point n0, it never decreases. For a function Hn, if h c times n is in theta Hn for any positive constant c, then Hn is called theta invariant under scaling, because we are talking about multiplying it by a constant. That's why we use the term scaling here, okay? Its theta class doesn't change. That's why it's theta invariant. When we scale it, meaning when we multiply it by a constant, its theta class remains the same, okay? And theta Hn, oh çok güzel. Bu eksikti. Uzatma kablosu gibi bir şey görüyor musunuz burada? Böyle anlatacağım artık. Okay? Theta invariant under scaling. And theta Hn is called a scale invariant class. Teşekkürler. Class. It's called a scale invariant class. So, let's see some examples for this, okay? For example, think about Hn is equal to n squared. So its theta class is obviously theta n squared. I don't even need to ask you to wake you up, okay? Even when you are sleeping, you can answer this. So what about Hc times n? What's its theta class? It's equal to c squared n squared. C was a constant, so does c squared, okay? So again, it's in this theta class. So no matter I multiply it with a constant, its theta class doesn't change. So it's this kind of a function. So for this kind of a function, I will be able to say that it's a theta invariant, okay? So another example, let's see. Hn is log n, which is theta log n, right? That's the function we had in binary search. Remember? So what about Hc times n? It's equal to logarithm c times n, right? And that is equal to log c plus log n, right? So c was a constant, so log c is also a constant. So this is still log n, right? So logarithm is also theta invariant under scaling. Is it clear for both the online class and the actual class?
Yes.
Okay, now we will see another example which is not theta invariant, okay? So I already gave you the answer, but we will see why. For instance, exponential functions, 2 to the power n, let's say. Its theta class is theta 2 to the power n, right? Obviously, that's its theta class. What about hc times n? What is it? Hc times n is equal to 2 to the power c times n, right? But it's 2 to the power c to the power n, right? So it's another class now. It's not theta 2 to the power n. 2 to the power n and 4 to the power n are not the same, for example. Okay, 2 to the power n and 8 to the power n are not the same either. So they are different theta classes. 4 to the power n obviously grows much faster than 2 to the power n, even though both of them are exponential. Okay? So it's not theta 2 to the power n. So 2 to the Cn is not in theta 2 to the power n. It's in theta 2 to the power Cn actually, okay? So exponential functions are not theta invariant. So another remark now. Suppose that bu burada şarj da olmuyor. Yani çalışan bir priz de mi yok bu sınıfta ya? Uzatma kablosu yok, hiçbir. Yani tabletin şarjı bitiyor. Nasıl olur? Efendim?
Fabrika işinize yarar bence.
USB girişi bilmiyorum. Şöyle bir şey kullanıyorum ama şöyle bir çıkışı var. Ben bilmiyorum. %14 aslında şu anda. Dersi idare edebilir, etmeyebilir. Tamam, giriyor galiba. Tamamdır. Tamamdır, çok teşekkürler. Arkadaşlar lütfen aşılarınızı olun. Bir hibriti daha bir dönem çekemeyeceğim. Yani bu sizin için de iyi olmayacak sonunda. Yani çıldırmak üzereyiz biz hepimiz hocalar olarak. Suppose that f b to the power n is in theta g b to the power n for b greater than 1 and n is in the set of natural numbers. Okay? So suppose also that, I will continue with here. Suppose that Fn and Gn are eventually non-decreasing and Gn is theta invariant under scaling. Okay, then Fn is in theta Gn for n being the natural numbers. Okay, I didn't write it properly, but this is the set of natural numbers. Okay, so if Fn and Gn are eventually non-decreasing, okay, if both Fn and Gn, if we show that both Fn and Gn are eventually non-decreasing, and in addition, if Gn is theta invariant under scaling, then we can say that we can generalize this for the general inputs, and that's what happens in binary search. We will see that binary search conforms with this case. Okay. Bir arkadaşınız chatten bir şeyler yazmış. İyi, eskide kalmış. Obsolete. So that's why we could, if we knew this beforehand, we could immediately conclude that this can be generalized for all inputs in binary search. Okay. Example. And that's the example we have in binary search. Wn is theta log n for n is equal to 2 to the power k minus 1. Okay. Let's check now. First, Wn is non-decreasing. Okay. Okay. Because it's the worst case function in general. Worst case functions are always non-decreasing, because if I increase the input size, can things go better? No, it might stay the same, but most of the time it will go worse. Okay, it's not natural for the worst case function. It's worst case functions for all algorithms, always non-decreasing. And also logarithm n is also non-decreasing. It's a non-decreasing function. Logarithm function is a non-decreasing function. And we showed that log n is theta invariant under scaling. I'm not going to write that, but just theta invariant. We showed it in the previous example. So this means that therefore, we can immediately conclude, of course, after mentioning these, that Wn is in theta log n for all n. Okay? So that's why we could also use that instead of squeezing it between two terms that are of the form so to the power k and making some mathematical manipulations. By using this and by also verifying that it conforms to the statements here, then we can easily conclude that this is true for general n. Okay. Now I will continue with insertion sort. You remember it from your data structures classes, but I will also write its pseudocode and then we will analyze insertion sort, okay? So procedure, insertion sort. L1n, okay? I'm writing the pseudocode of insertion sort, not only for you to remember, but we will make our analysis by going through the pseudocode, okay? For I from 2 to n, remember what it was doing? Can somebody explain it to me, how insertion sort works? From the online class? Anybody who wants to explain how insertion sort works? Let's say with numbers 4, 1, 2, 3, 5, again, I don't know, 8, 7, maybe. How does it work, the algorithm? Nobody remembers?
I remember, if I can.
Okay, can you explain it for us?
First, the insertion sort will take 1 and take back to square 1.
Okay, this one.
And after that, it will go for 2 and do the same thing.
It will go for 2. You mean it will take this one?
No. It will take the number 1 firstly and take it to the index 0. And
The
after
first,
that,
let's say.
yes,
Okay.
it will take individual numbers and it will pass it beyond to the back until
Yes.
it's greater than the index before itself.
Okay, so it's like I start with the first index 4 and assume that this is also already a sorted array, including only one element. And then I take the second index 1 and insert it into its proper position into this previously sorted array. And eventually I obtain the entire array sorted. So it will put it, okay, 1 should come first, so it will become like 1, 4, 1, 4, okay? So this will be the sorted portion, let's say. So, and then it will check 2. Okay, how do I do it? I put 2 in its proper position and make it 1, 2, 4. And eventually I grow my list like that. Eventually I obtain the entire list sorted, okay? So that's how insertion sort behaves. So because in each iteration, first of all, I make a linear scan by taking each element one by one into account, okay? But in each of these iterations, I put this element in the previously sorted portion, okay, in its proper position. And to put it in its proper position, I also make a linear scan here, okay? So it's like two iterations in each other. So that's why we had n squared, okay? But now we will make its analysis more precisely. We will make a thorough analysis, okay? So for I from 2 to n, do this. I say that current is equal to Li, meaning the list element that I'm pointing to right now, my current pointer, okay? I start with 2, its first points to 2. And position is I minus 1, okay? So it's like the last element of the previously the sorted portion, okay? So now in this while loop, I put my current, the element that is pointed to by my current pointer, let's say, index, in its proper position. To put its proper position, I make a linear scan from the back to the front of the sorted portion, okay? That's why I make my position from I minus 1, and while position is at least 1, and current is less than L position, do the following. L position plus 1 is equal to L position, okay? So position gets position minus 1. So the thing is, if the current, the element that I'm pointing to right now is less than the element that is pointed to by the position index, then I switch them, okay? So I put it into, be able to put it in its right place, I go from backwards to the front. And I end the while loop here. And then eventually I make the following adjustments by writing that L position plus 1 is equal to current, and end for and, okay? So it's like we have an already sorted part. And this is the current. And I go from here to backwards. So we're trying to place the ith element in the proper position in the already sorted list, okay? We are trying to place the ith element in the proper position. In the already sorted parts. Okay, so that's how insertion sort works. You remembered it also. Now, best case. When do you think the best case occurs?
When the array is already sorted.
When the input is already sorted. Why?
Because it doesn't have to make any insertion.
Yes, it doesn't have to run anything inside of this inner while loop. Okay, this inner while loop always terminates, returns to false. So I will only make this outer loop. This outer loop is inevitable. Okay, this for. So I have to go. So in here, each iteration of this for loop takes constant time because I'm never going to go get inside the while loop. Because it takes constant time, the overall will be linear, right? So that will be the base case. So let's write that, the basic operation. This might be a good choice for basic operation. It occurs if the input is already sorted. So more precisely, my for loop is from I from 2 to n. Okay, so I have a summation from I from 2 to n. And in each one, for loop always executes. I make a constant operation. So that is actually becomes n minus 1, right? Which is theta n. So in its best case, it's linear. Okay. So what about in its worst case? What happens in the worst case scenario?
I think it will be sorted, but in reverse order.
Reverse order. And in that case, first of all, I will always enter this while loop, and I will enter it as much as it gets, okay, in all cases. Because it's reversely sorted, when I go from backwards to the beginning, I have to go through all to the beginning always, okay? Because I'm going from backwards to the beginning, okay? For each iteration of the for loop, the basic operation is executed maximum number of times. This situation occurs if the list L from 1 to n is already sorted in reverse order. Okay, so in this case, again, I will go from 2 to n. That comes from the for loop from the outside. Okay, I from 2 to n. And in each one, I execute I minus 1 times, okay? When I'm trying to place the ith elements in its proper position, because the already sorted list has I minus 1 elements, I make all the comparisons in those I minus 1 elements, so I make an I minus 1 comparisons in each iteration, okay? So that is what? Now I can change the index because I from 2 to n, I minus 1 is what? 1, 2, 3, 1 to n I, right? It's the same thing, right? I can replace I minus 1 by I. So 2 becomes 1, 2, n minus 1, sorry. Okay? And what is this? Can somebody tell me what this equals? Exactly. I sum up the numbers from 1 to n minus 1. What is it? Discrete mathematics? I don't hear you properly. Maybe because of the mask, or I don't know. Just louder, please. Yes, n times n minus 1 divided by 2 is the exact number of operations we get. in the worst case, which is theta n square. Okay? So we know the best case, which is linear theta n, and the worst case, which is theta n square. So we know what to expect from our average case, okay? Before delving into the complicated analysis, not too complicated, by the way. I think it's easier than the analysis for binary search, I think. Before delving into that, I know that I cannot hope for better than linear complexity, okay? Because that's the very best case, and it won't be worse than n squared because that's already the worst case. It's somewhere in between. That it might be equal to the worst case or even the best case. We don't know that, but it's not. We know at least what to expect, okay? So now the average case. In the average case, again, I need to take into account all these cases. That's why it happened with the input, okay? Bu arada bunu çıkardım mı ben? %8'e düşmüş çünkü ya. Şarj oluyor mu bilmiyorum ama. Anyway. Şarj oluyormuş gibi gelmiyor bana şu an powerbank'ten ama çıkarmışım herhalde ben yanlışlıkla anlatırken. Anlamadım neden çıktı.
Işık yanmıyor mu hocam? Öyle.
Bir ışık görmüyorum.
Or belki şarjı düşmüş olmasın.
Bu da olabilir. Neyse arkadaşlar daha fazla vakit kaybetmeyelim. 9 dakikamız var. %8 şarjımız var. Average case. So step 1. What do I do in my step 1? Step 1 of the for loop. In that case, I have it, okay, index 1, 2, and then until n, okay. This is the already sorted proportion. Because I have only one element, I can assume that it's already sorted in its own way, okay? It's a sorted list with size 1. So that's why my for loop started with 2. So I looked at the position, the element in the second position, okay? So what I'm trying to do to achieve here is place L2 into its proper position, right? Okay. And what do I do in the step 2? Okay, step 2 of the for loop. Now, I have already sorted the first 2 is already sorted, and I'm trying to place L3 in its proper position, okay? Into its proper position. Okay? And then in the step n-1, which is the end of the for loop, remember the pseudocode? It was from from 2 to n, okay? Now when I'm in step n-1, what happens? The first n-1 elements are already sorted. Okay, and I'm trying to place the nth element in its proper position, right? So place ln into its proper position. So how many steps do I have? I mean, once I do that in step n-1, then I'm done, okay? Once I have done that. So how many steps do I have here? I-1 steps, right? n-1 steps, because I start with placing L2 in its proper position. Placing L2 in its proper position, and then I ended up with placing Ln into its proper position. So I have made n-1. There are n-1 steps here. Okay. So let Ti be the number of basic operations at step I. And then we will take into account the probability that how many of these steps actually occur, because that depends on the input, okay? The number of basic operations at step I for 1, I, n-1, okay? So this is Ti. And the total T is T1 plus T2 plus T, n-1, and that is equal to I from 1 to n-1 Ti, okay? That is the overall number of basic operations. The total, the operations I get in each step, I sum them up and I obtain the total. But here, just keep in mind that these are not deterministic numbers. Each of these Ti's are random variables. And these steps are disjoint. And each iteration of the for loop is independent of each other. So these are actually independent and identically distributed random variables, IID. Okay, so average case n is equal to the expected value of these t. Average means the expected number of operations. So expectation, let's apply this expectation operator on this total summation I from 1 to n-1 Ti. Remember from your probability classes that expectation is a linear operator. So that means the expectation of the sum is equal to the sum of the expectations. Okay, that's what a linear operator, that's what it being a linear operator implies. So I can sum I from 1 to n-1 expected value of Ti, okay. That is actual to equal to expected value of T1 plus expected value of T2 plus expected value of Tn-1, okay? Maybe in the best case, for instance, these expected values are only 1 maybe, okay? Because we only expect 1 operation in that iteration because it's sorted already. Or we expect n-1, n-2 operations because it's reversely sorted. But in general, it's a random variable, okay? We don't know how our input is. So it could be anything between the best case and worst case. So we need to, once we find this expected value of number of operations in each iteration I, then we can find this average case by summing them up, okay? For all I. So calculating expected value of Ti is our main goal. Okay. Expected value of Ti is equal to summing J from 1 to I %5. Bir dakika kaldı. J times, ya şunda bir sıkıntı var bilmiyorum ama bundan da ışık gelmiyor. Neyse teşekkürler, yine 1-2 dakika işe yaradı da. J times probability that Ti is equal to j, okay? And this probability is probability that there are j comparisons in the ith step. Okay? So, probability that there are j comparisons in the ith step times the number of comparisons, which is j. If I sum them up, then I will obtain the expected value of operations, expected number of comparisons in Ti, okay? Expected value of Ti. So next week we will continue with, from this point onwards, saying that, okay, in which interval does it fall into? Is it between L1 and L2? Is it less than L1? Is it greater than L1? And how many comparisons do we have in each case? Because it happens with equal probability that falling into one of those n+1 intervals, okay? But the number of comparisons in those intervals are different from each other. So we will keep manipulating this formula and see what happens. Thank you very much. Powerbank için de teşekkürler. Bize 2-3 dakika kazandırdı sanırım. Ha, o benim. Belki de bir sıkıntı var. Bilmiyorum. Devamlı bir şeylerde bir converter'larım var yani. Şunun için converter'ım, onun için bir şeyim.
Işık yanması.
Bu benim şeyimdi değil mi? Çıkış şeyim. Belki de öyle bir şey var.
Işık yandı.
Yanıyor evet. Bunda bir, belki de bu buraya da o yüzden bağlanmadı.
Hocam bu arada merhaba.
Ha, merhabalar, merhabalar. Yeni bu hafta başladım herhalde.
Evet.
Ben şu şeyi kapatayım da bir dersi. Ne yaptım ben? Bir dakika.